to what's the difference between just chemical equation, normal chemical equation, and thermochemical equation. And then how to cut. For the first part, we also discuss about enthalpy, how to calculate enthalpy by using Hess law. Okay, so these are the objective for the first part. Yeah, for the first part of thermodynamic or thermochemistry. So as usual, if you have any issues, you just stop me and ask me questions, okay? Right, so let's go to the basic one, okay? Introduce you what is thermodynamic or thermochemistry all about. So in kinetic, we are talking about the effect of time, okay? The effect of time and the effect of concentration towards a certain chemical reaction, okay? So we discuss in kinetic, if we have how the concentration reactant is affecting the chemical reaction based on the order of reaction, okay? So certain reactant has different order, and different reactant has different order towards that particular chemical reaction, and as well as time, also temperature. So that was discussed during kinetic, okay? And now, this is another part that is very important that is affecting chemical reaction as well, okay? So these two, kinetic and thermodynamic, okay, is very important for you to understand the fundamental so that in future you know how to manipulate, how to control chemical reaction, even though if it is large scale. So we start with some common terminologies, okay? Just a moment, yeah. Okay, so energy definition, energy is the ability to do work and supply heat. So in thermodynamic, this is very important. The relation is energy equal to, let me show you. Where is it? Oh, it's far, very far. Okay, the energy, okay, delta E, change in energy, is equal to Q, which is heat and work, okay? So that is the basis. That is the basis of what we're going to discuss until enthalpy. Energy, the change in energy is converted, is equal actually to work and heat. Okay, so from now on, we imagine that we are the entity. Okay, so imagine that we ourselves is the entity, and the energy change for our body, okay, is equal to work that we do. You're walking, you're eating, your whatever work that you do, as well as heat that is generated by your body. Now, of course, we are in, today is very warm, yeah? It's very hot, okay? So imagine now the energy change, whatever energy change happening is balanced, is total up, partly you translate it into work done by you, unless you lie down 24 hours, then probably the work is less than the heat supplied, okay? So now work is motion against an opposing force. Of course, this is just to define what is work. Yeah? Work is motion, means that something is moving, expanding, or being suppressed. Okay, is dynamic. Yeah, work is dynamic. It can be expanding, it can be suppressing. Okay, but it will have a change in terms of moving, or it might be contracting. Okay, so work is motion against an opposing force. Yeah, and kinetic energy is the energy, okay, has because of its motion or dynamic. Okay, okay, I'm sure that you are very familiar with the kinetic energy formula here. Okay, which is not really important for at this moment to discuss, just to show you the relation between mass and velocity. Okay, so the first law of thermodynamic, okay, this is very famous. Energy cannot be created or destroyed, okay, but it can be converted into from one form to another form. Okay, that's very famous. Okay, it is called law of conservation of energy. Cannot be created or destroyed, only to be changed in different form. Okay. Okay, so you can see that this is an example of how the change of energy, transfer of energy, okay, where the energy is not lost, but it is being transferred into another entity in this case, yeah, because we have different atoms, A and B, okay. So that's why, so this is related to the first law of thermodynamics. Okay, just now we discussed about kinetic energy. So it's about dynamic, it's about movement. But when we discuss about potential energy, it's about position of that entity. So if you are at third level compared to those who are at the ground level, means that you have a potential energy different from those at ground level. And also we have potential energy if we talk about arrangement, especially, for example, arrangement of atoms. This is a potential energy, arrangement of electrons. Okay. So this is also very familiar with you. This is during your secondary schools, the conversion between potential to kinetic, at which point you have maximum potential energy, at which point that you have all the potential energy is converted into kinetic energy, and so on. This is very famous diagram. Yeah? I think you have learned it in secondary school. Okay, this is also another very familiar when we are using spring. Okay, right? Fully extended, partially, and then fully compressed. Okay. So there is a process of conversion from potential energy to kinetic energy as well. Depends on the condition of the spring. Okay. So this is not really important, but for you to understand what is kinetic energy and what is potential energy. Okay, now, just now I asked you to imagine that you as an entity have a different energy, have a change in energy, and that change in energy is related to how much work and how much heat generated by you. So each entity, okay, including us, has what we call as internal energy. Okay. So the energy that is transferred as heat comes from objects' internal energy. Okay. Molecular kinetic energy. So this is again talking about the conversion of the kinetic energy to heat, okay? Right? And I'm sure that you are familiar with this, okay? The Maxwell-Boltzmann distribution, okay? Number of molecules that has a specific amount of energy is equal to the area under this curve, right? So now they are talking about average kinetic energy of its atoms and molecules. So let's say if you have a system that is with okay, certain specific kinetic, the internet, all right, specific kinetic energy, then you can see the fraction of the moles, okay, is here. And then for purple one, this is the amount. Okay, I'll change the color. So you can see that they have different amount of fraction of the molecules that have specific amount of kinetic energy at different temperature. So imagine that this T1 and then we have T2. Okay. All right. Now, so this is a process. This is just to share with you the process of how heat is transferred. Okay. So if you touch a very cold thing, you have a certain heat. Remember that you are also we are an entity with change of energy converted into work as well as heat. Let's say you touch a very cold object, okay, and then your heat will be transferred to that particular object. So let's say you are here, you are warm object, and then the cold object is the right one, okay? So the heat transfer will continue, the heat transfer will continue until the system achieve equilibrium, okay? So what happened is when the system achieve thermal equilibrium, okay, there are other equilibrium as well, like concentration. When it achieves equilibrium, then you can see that both kinetic energy of molecules in both objects are now similar. Okay. So the heat will be continued transferred to the colder object until you achieve this situation where the kinetic energy for molecules, let's say from you, the warmer subject, to the colder subject that you touch until it achieves equilibrium. So that is what is happening when heat is transferred due to energy difference. So if you look back at the plot just now, okay, you can see this is the relation if you have different, what happened to the kinetic energy, okay, and the amount of molecules that have that kinetic energy at different temperature. Okay, the energy of an object depends only its current condition. Okay, this is just to explain to you the meaning of state function. Okay, so the meaning of state function is it doesn't depend on the pathway. Okay, let's say you want to go to KL. You are from UPM and you wish to go to KL. You can have different routes. Okay, you can follow different routes, but internal energy means that It doesn't care about what routes that you chose, but it is the difference. The shortest difference, for example, is what is related to the internal energy. So if you look at here, what does it mean? Okay, state function, they are independent from the mechanism or method by which a change occurred. Means that what is the pathway, how the change happened will not affect the internal energy. Okay, what that the value depends on the change only. It doesn't depends on the pathway, how it changed. So easy to understand here. This is let's say you have the energy, the early energy, and this is the energy after some heat and work is done. So you remember that delta E is equal to Q plus W. Okay, so it might be E2 minus E1. Okay, so delta E or internal energy does not care about how, but it will be equal to the difference. Okay, so you might have more Q, for example, or you might have more work done, for example. It doesn't care, because in the end, what is state function, that is the difference. Yeah? What is important for internal energy is the difference. So you might have more Q, you might have more W. So this is what we call as state function. So heat and work are not state functions. They depend on the path between final and initial state. Yeah. Right? Heat and work depend. Both paths give the same value for internal energy. Okay. This is for internal energy. Okay. Means that it doesn't be affected whichever that we want to do. We want more Q or less W, or we want more W or less Q. But in the end, we will have the change. But Q and W is not a state function. Means that the whatever Q and W change will depends on how the process. Yeah, Q and W is not a state function. Okay. So very important to understand first, delta E is equal to Q plus W. That is very important. And then just now we learned about state functions. Okay, what is state functions? What is it's not a state function. Okay. And some more terms. Okay. The object. Okay. Just now I mentioned that let's imagine that we are the subject. We are the object. So we are called the system. It's easier to understand us because we do work and we generate heat. Okay, so the energy change of the system of us, some of the energy is converted into Q, some into W. So we are called the system. Remember that, easier for you to understand. You yourself is called a system. Now, if you sit inside a room, okay, if you sit beside an air condition, close to air condition, okay, or you might be sitting close to an oven in that particular room. Let's say you work in a bakery or you work in a cafe that you have to cook, okay? So those are surroundings. You are the system, and wherever you are, whatever situation you have what we call as outside system called surrounding, okay? And the system and the surrounding that surrounds you, it is called universe. Okay. All right. Okay. So now, that is very important to understand. Okay. So just now, just to extend to you this concept. Delta E is equal to Q plus W. Before we move on, we have to grab this idea that if Q heat is absorbed, okay, the sign is positive. The sign is positive. If Q heat is released, then the sign is negative. So work is done on the system. Okay, what does it mean work is done on the system? Just now we have a spring. So if the spring is compressed, let's say the spring itself is the system now. And if the spring is compressed, then it is done on the system because the system is the spring. So I don't want to give example, you being compressed. So now the system is spring. So work is done on the spring. Okay. Let's say now, if the spring, you release the spring and then it expands, right? It expands. So now the work is done by the spring, by the system. So the sign for work done on the system is positive, work done by the system is negative. So work is something dynamic, means something has to move. Then it is called work. If it is not work. And work is the formula, okay? I don't remember physics, but this is when we discuss thermodynamic or thermochemistry because we are discussing about volume change. But so the work formula is pressure times volume, the change in the volume, okay? So the movement will be the change of volume, and then the work must be based on the pressure, okay? If not, then there is no change of volume. So you can see that from Q plus W, we can change the formula now. Delta E, the change in internal energy or energy, is Q heat, and this one. So do not worry about the negative sign or positive sign because it will change throughout the question or throughout the scenario will change, depends on all these situations. So we have to consider whether this is going to be negative sign or positive sign, then we will decide on this method, okay? So do not worry at this moment why I put negative. Here is just an example, means that the work is done by the system. That's why it is negative. If the work is done on the system, then the sign should be positive, yeah? Okay, right. Okay, now let's do some question. Okay, the first scenario, spring is compressed and heated. Okay, so the Q is positive or negative?
Positive.
That is Q. What about work?
Positive.
Positive.
Okay, so spring is compressed, work done on the spring, and it absorbs heat. Okay, right. So B, Q is?
Negative.
All right, okay, release heat to the surrounding, okay. So work is?
Negative.
All right, expand, work done by the system. C, a spring is compressed and cooled.
Q negative.
All right, I think you get it. Okay, compress.
Positive.
Okay, that's good. Now we have learned about systems, surrounding, and universe. Okay, so now there are a few more terms: open system, closed system, and isolated system, or it is called adiabatic. Not diabetic, adiabatic. Okay, so what does it mean when you have open system? Okay, I usually give example of if you are cooking something. If you are cooking curry or tom yum. So the first scenario, you have the lid off. The lid is taken off. So this is the lid is taken off. So whatever here, if you leave it after 1 hour, then it might lost half of it. Okay, the curry now is half of the amount of the original or whatever that you're cooking. It's not because your friend take it, but it's because of the evaporation process, because it is an open system. So let's say you have a closed system. All right. So you have the lid on. Okay. So you're cooking curry and tom yum after 1 hour. Okay. The content is still there. You have a very tight lid on. So the content, it is still there. So no vapor, considering no vapor out. Okay. So the content, it is still there. But the energy or the heat of that food is now gone. Yeah? You just leave it for 1 hour. It is still warm, for example, but no, you turn off whatever heat. Okay. So the content inside the pot is still there, still same, but it has lost its energy, or it is now a cold curry or a cold tom yum, right? So that is closed system. Now you have a third system where you have let's say you have a very isolated, usually thermos, okay, that will block the transfer of heat, okay? So in the end, you will have the content, of course, originally, and the food inside that is still warm, okay? Because the energy is prevented from transferred, okay? So that is called isolated system, yeah? Okay. This one is just what we talked about just now, the negative and the positive sign. Okay, this one let us discuss later. Okay. So let's look at the learning objective, what we have discussed. Okay, some terminologies. Okay, very important for you to remember the delta E, Q plus W. What is Q? What is W? Of course, you have to understand the kinetic energy, meaning the potential energy as well. And then we have discussed about the state function, okay? And we also discussed about system, surrounding and universe, and an open system, closed system, isolated system. Okay, we also discussed about first law of thermodynamic. Energy cannot be destroyed, and it also cannot be created, but it can be transferred or transformed into different energy or transferred to another entity. And now we are looking at to solve calculation. Okay. Okay, solve calculation. So now, of course, we are talking about heat first, okay? Because in thermodynamic, the important is the heat. Yeah, we're not talking about the work, right? So heat capacity. So of course, you have to define what is heat capacity first. Heat capacity is the amount of heat, definition is very important, needed to raise the object temperature by 1 degree, and this is the unit, okay? Okay, this is another extensive property that can be determined from experiment and is proportional to the sample mass. So this is the formula. Heat, which is Q equal to C. C is heat capacity times delta T. T is temperature change. Yeah? In this case, it should be capital T for you not to be confused with time. Okay, should be capital T. So this is definition, the amount of heat needed to raise the object temperature by 1 degree and has the unit of joule over Celsius. And now this is specific heat capacity. Okay, it's unique. Okay, just now, just heat capacity, and then you can run experiment, and just from the experiment, you can calculate the heat capacity. But now, specific heat capacity is involving mass. Okay. So Q, so the symbol is S. Okay. So specific heat capacity is heat capacity, capital C just now, over mass of that particular material. Okay. So these are examples, okay, of unique property of certain material. Okay, so this is tabulated value, means that you can find it, what is specific heat capacity for copper, gold, or any other material. It has been tabulated. Okay, so you can use this formula as well. Just now is Q heat capacity times delta T. So Q now is MS, which is C times delta T. Okay. So let's say we look at example, the temperature of 250 grams of water is changed from 25 to 30. How much heat was transferred to the water? Okay, so now since you have a specific mass, okay, so Q is MS delta T, so mass, specific heat capacity for water, okay, and then the change in temperature. So you can calculate the heat transferred from the source of the heat of the heater, whatever they use, transferred to water. So this is the amount of heat being transferred to the water. Okay, this one is, if asked, then you have to tell whether it's positive or negative. Okay, so this is just an example. Of course, we're going to discuss more questions on calculation on Thursday. Yeah? Okay. All right. Okay, now. Okay. Right. So now we look at thermochemical equation. Okay, now we are going to focus on chemical reaction and the heat of the chemical reaction. Okay, just now we are talking about just a very general system, a general entity. We're not specifying on chemical reaction. Now we are moving to a chemical reaction. Is the heat of the chemical reaction. Okay, remember we are talking about the heat. Yeah? Right, now where does the heat come from, or where does the energy comes from? Okay. And this, of course, we have learned that the electron has its specific energy, okay? And when the chemical bond happen, yeah, there is a energy release, okay? And some chemical reaction requires energy to be absorbed, okay? So all these chemical reaction involve a lot of energy. It can be positive, it can be negative, okay? So the attractions of the electrons for the nuclei, okay, in this case is hydrogen, H2, is strong enough to overcome the nucleus and electron repulsion. So everything, okay, you imagine that in order for the hydrogen molecule, H2, to stay as hydrogen molecule, it requires certain energy to stay there. Okay, remember that this electron cloud is being attracted to the nucleus as well as here. And it also has repulsion. So lots of energy has to be there in order to stay as hydrogen molecule. So this is just example. So when you break the bond, you might have energy release. Okay. So the potential energy that resides, that is in the molecule, you have to imagine a bit that electron, in order to stay here, again, has to maintain certain potential energy to stay there. Yeah? So if you break the bond, then the energy will be released. Remember that the first law of thermodynamic, that the energy will not be destroyed, it will be transferred, it will be transformed. Okay, so that energy will be transferred, will be transformed into chemical energy. It can be released, or the system might be absorbing more energy. Okay, so during chemical reaction, there are certain chemical bond that is broken. Okay, as for example, for the reactant, the chemical bond will be broken, and the product will form a new bond. So there's a series of probably energy being absorbed, energy being released, okay, during the process, okay? But very important for you to understand, where does the energy comes from is the potential energy from the electron to stay there, to be at the position that the electron is supposed to be, okay? So that is happening in you, in us. How come do we have enough energy to study? How come do we have enough energy to do things and to maintain a specific certain heat so that we're not that cold? So the biochemical reaction that is happening inside your body is the one that that is being transformed into heat as well as work. Okay, and that biochemical energy, biochemical process that transform energy, and the energy comes from the electron inside the atom in your body. Okay, this is what I have discussed just now. Chemical reactions involve both making and breaking chemical bonds, and those making and breaking chemical bonds will result in the energy difference. Okay, it might gain or it might loss of energy. It might release, it might absorb. Okay, so this one you are very familiar with. Heat is produced, exothermic. When energy or heat is being absorbed, it is endothermic. Okay? Okay? So how do we measure the energy of the reaction? Okay? People talk about calorie. So how much calorie if you consume pineapple tart? Okay? So how much energy do you consume if you eat a burger? Okay? So that is chemical energy of that particular food. Okay, how do we measure? So we have what we call as calorimeter. Okay, so this is example of calorimeter. Yeah, it is called bomb calorimeter. And if you put in food here, and then you burn it, okay, so you can measure the heat of reactions. And these represent the calorie of the food that we consume. This is an example that I'm giving example of food. Yeah. And why we use, there is a specific example, we have to use specific calorimeter because we have to control that whatever chemical reaction happening in the food, when we burn it, it will not be changed into volume because we want to measure, let's say this is E, remember, chemical energy from that particular food. It might change into W, okay? But we will, the setup of the calorimeter, based on the setup of the calorimeter, now we can control that the Q heat is now equal to the total of the chemical energy from that particular food, right? So you can see it is heavily insulated, okay? So that there is no volume change. So the heat released by the combustion of that food will be absorbed by the bomb and surrounding water. So this is water. So we can measure how much energy transferred to the water is equal to the energy released by that pineapple tart. Okay? Okay, that's how much calorie that will be obtained from that. Okay? All right. So there is a special terms that we use when we are talking about heat of reaction. Okay? Okay? So just now, it's actually a chemical reaction. Yeah? That's why you receive heat from the pineapple tart. Okay? Now, that heat of reaction is known as enthalpy. Okay? So whatever chemical reaction that we do or is happening in our body, the heat that is absorbed or that is released, it is called enthalpy. Okay. So again, we have this negative sign, positive sign, depends on the process, whether we have absorbed or a release process. Okay. So very important, if you look at here, okay, it goes back to the one that we discussed just now. Okay, so now the original equation is now being rearranged, that Q is now called enthalpy. Okay, Q now it is called enthalpy because now we are talking about heat of reaction. So enthalpy is actually Q and is actually heat of reaction. Okay, so this is just some terms that you have to know. Okay, what is the meaning of standard heat of reaction? Okay, so it is still heat of reaction, but the value of enthalpy change under standard condition. Okay, involving actual number of moles. Okay, this is standards. Okay, okay. And for standard enthalpy, we have what we call as H naught, delta H naught. So when we have this delta H naught, means that it is a standard enthalpy. Okay. So you can find out about, for example, this is the reaction between nitrogen gas and hydrogen gas. Okay, you can see the molecule N2, H2. So when you have a balanced equation, okay, there is a tabulated value of standard enthalpy. Means that if the reaction is balanced, okay, you can use this value of standard enthalpy. Okay. Now you look at here, very important. If you reverse the reaction, here ammonia now is the reactant, then the value of enthalpy is the same, but now it is with positive sign. Okay. And the chemical reaction with the value of standard enthalpy, the whole thing it is called thermochemical equation. So the difference with just normal chemical equation and thermochemical equation, that thermochemical equation should have this, yeah, standard enthalpy. So that is thermochemical equation. We're not going to discuss enthalpy diagram, okay? Okay, so the last part for the part one is to discuss the use of Hess law. Okay, so it's quite simple. We can calculate enthalpy by using Hess law. So what is Hess law? Okay, this is Hess law. Just a moment. Okay, so this is Hess law. Okay, in equation form, but in definition form just now, the value of enthalpy change for any reaction that can be written in steps equals the sum of the values of the enthalpy change of each individual steps. We have it. Okay, so the enthalpy change, standard enthalpy change for that particular reaction is the sum of enthalpy change of the products minus sum of the enthalpy change of the reactant. So if we look at here, the example, calculate the enthalpy of reaction for 2 nitrogen monoxide plus oxygen forming 2 nitrogen dioxide. So the enthalpy change, okay, is the sum of delta H naught for product. So product is 2 NO2. So we can find it from the table, okay? Since the stoichiometry is 2, so we have to use 2, okay? Minus the sum of delta H naught of reactant. So we have 2 nitrogen monoxide. So remember the 2 and 1 oxygen. So here, okay? So we can just put everything here, then we can get the total of delta H naught for this reaction. So that is how we use Hess law. Okay. All right. Any questions before we take a break?
No, I think.
Okay, so we take a break for 10 minutes. Okay, so I think around 3:05 or 3:07, then we start back for the second part, which is entropy and Gibbs free energy. Okay, all right.